The concepts of the golden ratio, Fibonacci sequence, and continued fractions have been a crucial piece of knowledge in mathematics, with some of them dating all the way back to ancient Greece. In this video presentation, I will go over the history of those three concepts, along with how they're related to each other. Starting off with the golden ratio, 1.618, which was first described by Euclid in 300 BCE as the division in extreme and mean ratio. In Book 6 and Proposition 30 of Euclid's Elements, he has a line of length 1 with the points A, G, and B. The length of AG is G, so the length of BG is 1 minus G. He described the ratio of BG to AG equals the ratio of AG to AB. In other words, the ratio of the two divided length equals the ratio of the longer length to the whole line. He then plugged in the length and got 1 minus G over G equals to G over 1. This can be rearranged into this. And using the quadratic formula, we find that this equals to 0.618 or negative 1.618. The solutions here give us the negative of the golden ratio and the golden ratio minus 1. In modern notation, 1.618 is symbolized as phi, the golden ratio, and 0.618 is symbolized as little phi. Fast forwarding a few hundred years to somewhere around 850 to 930 CE, where Egyptian mathematician Abu Kamil used phi in his work on the pentagon and decagon to calculate geometrical problems. This may have inspired Fibonacci in 1170 to 1250 CE, who developed the Fibonacci numbers. The first known decimal calculation of phi was in 1597 by Michael Maslin in a letter he sent to Johannes Kepler, who was his former student. In the letter, Maslin calculated phi to be 0.6180340, which isn't too far off from the actual value. Kepler then used this knowledge in the same year to describe Kepler triangles, which are triangles with side lengths that follow a geometric sequence, with the common ratio being phi. Finally, the term golden ratio was coined by Martin Ohm in 1835 as Goldene Schnitt, translated to golden section. Then, the golden ratio was represented by Greek letter phi in 1910 by Mark Barr. So now moving on to the Fibonacci sequence, which is of course described by Fibonacci himself, whose real name is actually Leonardo Pisano Bigoglio. The Fibonacci sequence is a mathematical sequence in which each number is the sum of the two preceding ones. The first numbers in the sequence are 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on. We see that 0 plus 1 is 1, plus 1 is 2, plus 1 is 3, plus 2 is 5, and so on. Interestingly, the sequence actually predates Fibonacci by quite a few centuries, all the way back to around 450 to 200 BCE in Indian mathematics. In the Sanskrit poetic tradition, long syllables of 2 units duration and short syllables of 1 unit duration are mixed to create the poetic verse. Upon closer inspection, it can be seen that the duration of successive long and short syllables actually results in a pattern identical to the Fibonacci numbers. This can be traced back to Acharya Pingala, an Indian poet and mathematician. In 1202, Fibonacci sequence first appears in the book Liber Abaci by Fibonacci, accompanied by an example with a rabbit population problem. Suppose we have pairs of rabbits that don't die, and after 2 months of maturation, the female rabbit produces a new pair of male and female rabbits every month. In the beginning, in the first month, we have only 1 pair. In the second month, the first pair is mature enough to produce a second pair. In the third month, the first pair produces another pair, making 3 pairs total, while the second pair is still maturing. In the fourth month, the first and second pairs of rabbits produce a new pair, making 5 pairs total. As the months go by, the numbers of pairs will be 8, 13, 21, 34, and so on, following the Fibonacci sequence. Lastly, we have the continued fraction, which is an iterative process of having the sum of an integer and a reciprocal of another integer. This can go on infinitely, but all the integers involved, except for the first one, must be positive. This was first mentioned by Euclid again in 300 BCE in Book 7 of his Elements, in the form of finding the greatest common divisor. Moving on a few centuries, in 499 CE, Indian mathematician Aryabhata used continued fractions to find general solutions of by equals to ax plus or minus c. Then, in 1572, Raphael Bombelli used continued fractions to calculate square roots, as he proved that the square root of 13 is 3.605550883. This isn't far off from the actual value of 13. Next, in 1613, Pietro Antonio Cataldi was credited as the person who used the first proper notation for continued fractions, and the term continued fractions was established by John Wallis in 1695. So now to bring it all together, as the numbers in the Fibonacci sequence get bigger, the ratio of each consecutive number actually gets closer to 5, even though Fibonacci himself didn't intentionally plan this. With continued fractions, we can use the definition of the golden ratio, which is this. We can then rearrange it to be this. Then, we can substitute 5 by itself in the denominator, giving us this. We can do this infinitely, giving us a continued fraction. I think those three things are quite important because we do see the golden ratio a lot in nature, from something as small as a snail shell to as large as the Milky Way galaxy. Some studies say that the golden ratio may also be the most pleasing to the eye as we prefer shapes that follow the golden ratio. For example, a golden rectangle looks like this, with Euclid's original proposition of the golden ratio as comparison. We see a lot of this in architecture. Whether it is intentional or not, I find this quite fascinating. And there we have it, a brief history of the golden ratio, Fibonacci numbers, and continued fractions, and how they are related to each other. Thank you for watching my presentation.